Okay, so today we start with the common collector amplifier. Before we start, I leave you with a quotation. Think about it. Today's problems are a result of yesterday's solutions. That's a very general statement. And think about how it applies to various issues. But for us, the problem that we are addressing today arises out of the problems that we had seen earlier with common emitter amplifier. Okay? So this is how we're going to proceed. We'll look at, as I said, today's topic is a result of a previous topic, which was common emitter amplifier, specifically the problems with common emitter amplifier when you use it at the output stage, when you connect it to the load here. And as usual, whenever we take an amplifier stage, we look at its voltage gain, input and output resistances. We look at its voltage swing. We look at its frequency response. Okay. All right, so the first thing to realize is that common emitter amplifier by itself is not sufficient for many applications, and I'll illustrate it with an example here. This amplifier that you see here looks like a common emitter amplifier in some of its characteristics here. Its gain is reasonably high, voltage gain of 100, input resistance of 1K, output resistance of 1K here. Okay, one can call it as a typical common emitter amplifier. Now suppose I want to use this amplifier in an application which is given over here. Right? So what I want to do is, for my application, I'm looking for an amplifier that will give me a gain of 20 across a load resistance of 0.1K, 100 ohms resistance, and my source has a relatively high resistance of 10K here. Right? So this is the kind of an amplifier that I want to build with a high source resistance of 10K, relatively low load resistance of 100 ohms, and I want to get a gain greater than or equal to 20. Let's say there's some hypothetical application for which we require such a characteristics. Now, if I take this particular amplifier, let's say if I have a common emitter amplifier which is already designed to give me an open circuit gain of 100, input and output resistances of 1K. If I take this amplifier and plug it here, then what I will get is the following. I have my source here as usual, 10K. The amplifier has been substituted by its model here with an input resistance of 1K, and open circuit gain is 100 times V in, output resistance is 1K, so we've substituted it here. So that's my amplifier in, with these three quantities here, and a load of 0.1K. So if I put it together and I calculate what the overall gain is, this output voltage divided by Vs, it's a case of simple voltage dividers, I get a gain of 0.826. I don't get any gain at all. I was looking for a gain of 20, and all I get is a gain less than 1 here. And so what it says is that there's a mismatch between the characteristics that I have and my source and load resistances that are given over here. Okay. So what it is pointing out is that a typical common emitter amplifier that you see here is not going to work very well with if my source resistance is very high, relatively high, or if my load resistance is relatively low. It's not going to work very well. It will not be able to build up sufficient gain here. Okay. Of course, there are many ways of designing common emitter amplifier here. I could have built up, for example, all of you know there's a trade-off between gain, input, and output resistances. I could have designed an input resistance of 10K, output resistance of 1K, and then the gain would have fallen to 10. The gain would have fallen to 10, and obviously, if the open circuit gain is 10, I cannot get a gain greater than 20. So that's impossible. So there are various ways in which you can design common emitter amplifier. What you would find is, in general, you will not be able to satisfy these specs that you see here. Okay. So the idea is that if I have low values of load resistance, high values of input resistance here, my common emitter amplifier doesn't work very well in that situation. All right. Now suppose we have an amplifier with a characteristic like this. Let's say hypothetically an amplifier exists whose open circuit voltage gain is 1, input resistance is 10K, output resistance is 0.1K. Let's say an amplifier like this exists. Now the issue is, can we use it in our application? Not directly. Obviously, if its open circuit gain is 1, if you plug it here, it's not going to give you any gain. So that's obvious here. But so look at this amplifier. It has a high input resistance, relatively low output resistance, but doesn't give you any gain. Now the issue is, will an amplifier like this be useful? Well, one can see that if we combine it with the earlier amplifier, you'll see how useful it becomes here. So this is my earlier amplifier, common emitter like amplifier here, gain of 100, input resistance of 1K, output resistance of 1K. And that was the amplifier that I talked about earlier, gain of 1, high input and output resistance. So I put one stage here, and I put one more stage here. Okay, I use that particular stage. You can see why I'm using it. This amplifier has a low output resistance, which means that it has a greater ability to drive the load here. While this amplifier, again, that you see here has a high input resistance here, which means high input resistance means that is the impact of larger source resistance is negligible on this particular amplifier here. Okay, so if I do this now, I take my original common emitter like amplifier and add a stage like this here and add a stage like this here. If I work it out, what is the overall gain? I get a gain of 20. So what it shows is that this amplifier alone, if I had used it in my application, it was not giving me any gain. It was not giving me any gain. This amplifier by itself obviously is gain less than 1. But if you put them together, you are able to now achieve an amplifier which is much better than either this one or this one. Okay, this together, all this 3-stage amplifier that you see here, if I look at it, its overall input resistance looking from here, which is 10K. Its output resistance looking from here, which is 0.1K here. And open circuit gain, I don't have a value here. Open circuit gain would be, if I look at this particular amplifier, this is 1, this is 100, would be close to 100. So now together, if I use this particular stage along with a stage like this and a stage like this, I'm able to get an amplifier which has a high gain determined by the middle stage here, high input resistance determined by this stage here, and a low output resistance determined by this stage. Okay, so so then going back, a stage like this is a pretty useful stage here. Even though it doesn't build up voltage gain, it has a high input resistance and a low output resistance, and therefore it allows me to achieve gain and other characteristics which is not possible through use of a common emitter stage alone here. So the idea is that this is like a common emitter stage. This is the stage that we'll just talk about, a common collector stage here. And so the idea is anytime you're looking for a high input resistance, what you do is you take a stage like this and put it before. And therefore the combination, because it has a gain of 1, the overall gain remains the same as this stage here, and input resistance increases. So that's how you increase the input resistance here. If you're looking for a low output resistance, what you do is you take a stage again like this here, which gives you gain, and you put a one stage like this at the output here. And now the output resistance is lowered here. All right. So together you can see they're a very useful combination here. Common emitter followed by common collector, or a common collector followed by a common emitter here. Okay. All right. So we see that a stage like this is useful here. Even though its gain may be 1, its input resistance is high and output resistance is low here. So we are looking for an amplifier which will give us this kind of a characteristics, because we have just seen how useful such an amplifier can be here. Okay. So what are we looking for? Low output resistance, high input resistance here. The other thing that we are looking for is large voltage swing without requiring very large supply voltage here, because remember, we are thinking of this particular stage to be used at the output here, directly connected to the load. And therefore, swing will be important for a stage like this here. And along with swing, this is the stage that will deliver power to the load, because it's directly connected to the load. So we are looking for efficient operation, that most of the power is delivered to the load and not lost in the amplifier. Okay. So if you're looking for a stage which will give you low output resistance, then if you look at a transistor, we have seen earlier that if you look into the base, you see R pi. If you look into the emitter, you see R pi by beta, which is 1 by Gm. And obviously, if you look into the collector, you see R0. So if we look at all the different resistances, we see that the least resistance is here, if you look into the emitter. Then the next one is this one here. And then the next one is looking into the collector. So if you're looking for an amplifier which has very low output resistance, then you should take the output directly from the emitter. You should not take it from the collector, because at the collector the resistance is large. And so the choice then is taking it at the emitter. This of course is a large resistance here. And this gives you the typical numbers here. If I take my transistor, bias it at 2.6 milliamperes, beta is 100, early voltage is let's say 100 volts, 1 by Gm that you see here is only 10 ohms. R pi is 1 kilo ohm. So what you note here is there is 2 orders of magnitude difference between R pi and 1 over GM. And R naught for this value here, it turns out to be 40 kilo ohms here. So again, several times higher than this particular value here. So what we see here is that if you are looking for a low output resistance, you should take the output from here, from the emitter, because the resistance at this particular node here, if you look at a resistance at any particular node, it will be resistance looking left here or resistance looking right here. If the resistance looking left is 1 by GM, already very small, any resistance which is towards the right, whatever value it is there, it will come in parallel with 1 over GM and overall resistance will get lower. Okay, so this is the motivation for taking an output from the emitter here. All right, so here is an amplifier which does that. The biasing, as usual, is the same. R1, R2, RE, all these are used for biasing. And we don't need a resistance here at the collector. It's no longer required. Earlier, we were taking output at the collector, and therefore we needed a resistance here. Now we are not taking an output at the collector. We don't want any drop to take place here. It's unnecessary. So we've removed the collector here. Emitter resistance is there, and the output is taken here at the emitter node. So we take it through a capacitor, and we connect a load here. All right, so that's called a common collector. The input is applied. If you build a small signal model, you'll see that input is between base and ground here, and collector will be nothing but small signal ground here. And output will be taken between emitter and ground here, and collector is again small signal ground here. So you could think of collector, which is a common small signal ground, as a common terminal between the base and the emitter node, between the input and the output nodes here. All right, so small DC analysis we know already is the same. We don't have to discuss it again. The small signal model is again what we have done is taken the same thing here. I've included an RS here just for the sake of discussion here. RS is there in the source. R1 and R2, all of you know, becomes RB. RE is there, of course. Capacitor will become a short. RL will be there. So that's what you'll get here. I've included RBB also. We have said that under mid-frequency region here, RBB is not needed. For frequency response, this becomes important here, much more important here. All right, so this is the small signal model that we have. And I'm not going to go through the details here. One can write down the gain of this amplifier, V0 by Vs here. There are two terms that you see here. The first one is a loss here, because if you connect an RS here, you know that some signal gets dropped here. And so that's the loss. The signal that appears at this particular point here is given by here, 1 plus that voltage divider here. And then from here to here is this particular gain, beta plus 1 RE parallel RL. Again, as I said, in mid-frequency range, we have neglected RBB. It doesn't appear anywhere here. We have ignored that. And so that's the gain of the amplifier. What you note is if your source resistance were negligible, RS were negligible here, then this term would have been absent and this term would have been there. And if you look at the terms here, you note that the numerator is smaller than the denominator here clearly, and this term is also larger than 1. So gain obviously is less than 1 for this amplifier. Gain is less than 1, but under typical conditions, if you design properly, we'll see later on, this quantity beta plus 1 RE parallel RL is much larger than these quantities here, and therefore the gain is very close to 1. Okay, you can easily get gain of 0.9, 0.95, and so on. All right. Now, it's for this reason, if you note that gain is practically equal to 1, which means that V0 is practically equal to Vs, or very close to Vs. It's for this reason that we call this stage also as an emitter follower. As an emitter follower, because V0 is equal to Vs, it means that emitter here, emitter voltage, there's nothing but the emitter small signal voltage here. Emitter voltage follows the base voltage here. Okay, whatever happens at the base, if this goes up, this also goes up. If this goes down, this also goes down. It follows the base voltage here. And for that reason, we also call it this stage as emitter follower. All right, interesting issue is, why is this emitter follower being called an amplifier when its voltage gain is less than unity? Why don't we call a step-up amplifier step-up transformer and amplifier. The obvious issue is, as we said right in the beginning, to call an entity an amplifier, it has to have power gain. So this can step up the voltage, but the power gain will be less than 1. Some losses will be there in the transformer here. In this case, we saw that V0 is practically equal to Vs or a little less than Vs, but we'll soon see what happens is, if I look at it from here, the input resistance of this stage is going to be high. So what happens is, the current that goes from here, the current is small, which means that the power that is input into the stage here is small. While V0 is basically equal to Vs, and RL can be pretty small here, and therefore the power here, V0 squared by 2RL, is going to be pretty large here. So what we'll see here is that this power delivered to the load is much larger than the power that I take from the source here. And therefore, even though voltage gain is 1, it builds a power gain. It builds a power gain, and that's why we call it an amplifier, and even though voltage gain is less than unity. And this one, we cannot call it an amplifier. So necessary condition is power gain. All right, input resistance of this stage. So that's relatively easy to calculate now. We have seen that if you look into the base of an amplifier, this is a base of a transistor, and this is a small signal circuit. So what you see here is R pi between base and emitter node is R pi. The first term is R pi here. And the second term, whatever is connected in the emitter, Re gets multiplied by 1 plus beta. So we know now the input resistance looking from here will be this resistance RB. RB here in parallel with a resistance looking into the base here. And the resistance looking into the base is this one here. R pi plus beta plus 1, Re parallel RL, Re parallel RL here. So that's the first term here, which is resistance looking into the base. And the second term is, it comes in parallel with RB, and that's how my input resistance is. Okay. Output resistance is resistance looking from here. And in this case, we need to remember this result, that when you look into the emitter and you have some resistance connected in the base, the output resistance is going to be, the resistance looking into the emitter is going to be this Rs plus R pi, the whole thing divided by beta here. Beta or 1 plus beta. Sometimes we neglect 1 here because beta is large here. So output resistance then, looking from here, is going to be the resistance looking in the emitter node here. So when you look into the emitter node, you're going to see total resistance here, which is RB, parallel RS, and R pi. So let's see if this makes sense. The resistance, when you look into the emitter here, you see this one. R pi, which is this one here. RB parallel RS is the resistance here. RB parallel RS divided by beta plus 1. That's the resistance looking into the emitter node. And remember, when we say resistance looking into a node, it is the resistance between a node and ground. So because it's the resistance between this node and ground, it comes in parallel with Re, and so that's the next resistance here. Okay, so that becomes our R naught. And as I've been saying, it is this resistance which is small here. R pi plus RB parallel RS here, and the whole thing gets divided by beta, which is a large quantity here. So this resistance is small, and that is what, even though Re may be large, this is small, and that is what makes R naught smaller. Okay, so here are the values for us. We have all the gain here. A little bit of change of notation. Instead of RS parallel RB, we've called it RS dash. Re parallel RL, we've called it Re dash here. So we have gain expression, we have source output resistance expression, and we have input resistance expression here. So we have all these expressions. So what I'm going to do is, we know that in a amplifier there are trade-offs between gain, input, and output resistances. To bring out the trade-offs, I'm going to do a little bit of simplification here. The first thing we note here is, under typical conditions, gain is going to be 1. If I design it properly, the gain of this amplifier is going to be 1. The second one, I'm assuming that this quantity here, under typical conditions, will again be much smaller than Re. So my output resistance is going to be determined by the first stage here. R pi plus RS dash divided by beta plus 1. Now remember, when I'm doing all of this, my goal is not to obtain a quantitative answer. My goal is to obtain a relationship. And that's why I'm simplifying here. Rn, if I look at Rn here, Rn is, there is a term R pi, beta plus 1 Re dash. Because this term is getting multiplied by beta here, this term is going to be typically larger than this term here. So I've kept only the second term. And I'm assuming again that I've designed it in such a way that RB is larger than this quantity here. So we've written it Rn equal to beta plus 1 times Re dash. So these are simplified. If you want accurate answers, you go ahead and use this. But these are simplified equations, expressions which we will use to obtain the relationship between the quantities here. So gain is 1, so I don't bother with it. Rn divided by R0, then these are these quantities here. And these I can rearrange given the values that are there, Rs dash and all of that. I can rearrange in this form. Rn by R0 is beta ICQ Re by Vt here. And where is ICQ and all that coming? Basically because I have R pi here. So R pi will be Vt by ICQ times beta here. So it's taking these equations and rearranging them and writing, instead of Re dash, writing it Re parallel RL and all that. Rearranging it, we get Rn by R0 is beta ICQ Re by Vt 1 by 1 plus Rs dash R pi 1 plus Re divided by RL. Now the importance of this equation is as follows here. Suppose I were able to design it, my common collector amplifier, in a way such that, let's say, my Rs dash, input Rs is small compared with R pi. So this factor is close to unity, let's say. Maybe this factor is close to unity. Suppose it's there, we'll see later on. So if these factors are close to unity, then Rn by R0 is beta ICQ times Re divided by Vt. And ICQ Re is a large term. ICQ Re, is the drop across the emitter, and we keep the drop across the emitter for bias point stability. And so that drop is going to be at least a volt or 2 volts here. So this one, ICQ Re by Vt, can be a fairly large quantity. Vt is 26 millivolt, and this is of the order of 1 volt or 2 volt. So this is a large quantity here. Even though these terms may be greater than 1, what I'm seeing here is that this term is much larger than 1, can be much larger than 1. And therefore, Rn by R0 is equal to beta times a quantity which is considerably larger than 1. Now, why is that important? It's important, let me look at it here. Okay, it's important for the following reason here. We know that common emitter amplifier gives us voltage gain, input and output resistances, and we have seen that the trade-off between the quantities are AV into Rn by R0 is beta here. So, the first issue that arises is, I'm claiming that my common collector amplifier gives me high input resistance and a low output resistance and a gain of 1. Well, somebody can argue that I can get that from common emitter also. Because if you note that common emitter amplifier, if I make a gain practically equal to 1, then Rn by R0 is equal to beta. So I can get a large input resistance and a smaller output resistance here. But note, what is the capability of my common emitter amplifier? If you make gain equal to 1, it gives you Rn by R0 equal to beta. So its ability to provide large input resistance and small output resistance is basically equal to beta. And what did we just say about common collector amplifier? Rn by R0 is beta times some of these quantities here. And this remaining factor is larger than 1. So what I'm saying is, a common collector amplifier's ability to provide you with higher input resistance and lower output resistance is much larger than what you can get from a common emitter amplifier. You could take a common emitter amplifier, make a gain of 1. All that you could do is Rn by R0 will be equal to beta. Common collector amplifier will give you Rn by R0 equal to beta times a larger quantity. So this stage sort of specializes in giving you large input resistance and a smaller output resistance. You cannot get that from a common emitter amplifier. Let me give you through some example here. So here is a common collector amplifier. Using the expressions, we can now, so beta is 100, ICQ is biased at 3.4 milliamperes, VCQ is 6.5. Gain, note, using the expressions that you've derived, gain is 0.99, very close to unity. Rn is 13.4K and output resistance is 9.5 ohms. Very small output resistance, very large input resistance here. And now if I take this quantity here, AV Rn by R0, if I take this one here, turns out to be 1.4 into 10 to the power 3, which is equal to beta times 14. So it tells you now that gain is equal to 1, Rn by R0. The capability of this amplifier is measured by this ratio here, Rn by R0. I can, if you reduce R0, then Rn also has to be reduced because the right hand side is relatively constant here. So the capability of this amplifier is showing you Rn by R0 is beta times 14. While, as I said, if you take a common emitter amplifier, design it with a gain of 1, you would have gotten Rn by R0 at the most equal to beta here. So it shows you the capability of this amplifier. It has much greater ability to provide higher input resistance and a lower output resistance. Alright, so this was a standalone amplifier, common collector standalone amplifier. In the next case, what I've done is, I've taken this common collector, same common collector amplifier, but now it is being driven by a common emitter amplifier. Note that this is a common emitter amplifier here, and this output of this is going into my common collector amplifier. Okay. Now, the difference between the earlier common collector amplifier was, this was being driven by a source with negligible source resistance here. Now, of course, if I'm interested in this one, it's the same amplifier here, but note my source is what? If I look at it from here, source has a resistance of 2.2K. Why? Note common emitter amplifier that I see here. How can I model it? I can model it as at the output as a voltage source in series with a output resistance. And output resistance is nothing but 2.2K. So the whole of common emitter stage here has been modeled by a source here. Obviously, this source is not the same as this source here. Okay. So don't get confused by that. So the whole of common emitter stage is modeled as some voltage source in series with 2.2K, which is the output resistance here. So as far as common collector stage is concerned, the common emitter for it is nothing but a source and a resistance of 2.2K. Now the difference between this circuit and the earlier circuit was there was no RS here. Now there is an RS here. So if I redo the calculation, earlier also I had a 2.2K, so I get a gain of 0.85. Why is this gain dropped? Earlier it was 0.99, now the gain is 0.85. Drop here. 2.2K, some voltage gets dropped here, and that's why V0 by Vs is no longer 0.99, is 0.85. Input resistance is same as 13.4K. Output resistance is increased. Go back and see output resistance here was 9.5 ohms. You were looking into here, and so all these resistances matter here. And now when you look into here, you have this 2.2K. So output resistance goes up here, 27 ohms here. Even after all of this, if I do AV Rn by R0, it turns out to be beta times 4.2. So again, it shows you that this stage has a greater capability of providing larger input resistance and a smaller output resistance. So that's the special characteristics of this particular amplifier here. Gain is practically equal to 1, and the ratio of Rn by R0 is a larger quantity than beta. Alright, so we have seen its capability in terms of gain, input and output resistances. The next thing to look at is voltage swing here. So now voltage swing is, as usual, we have various constraints. Some constraints come from transistor should not go into saturation region. Other constraints come from harmonic distortion. So let's see one by one. So the first one is transistor should stay out of saturation region for my amplifier to work properly here. So now we are interested in this particular node here. So let's look at this particular diagram. So we have voltage along time axis. This voltage is VE here. That's the first one, VE here at this particular node. Now as I apply my input along with my DC here, I get a sinusoidal voltage here. Now note what happens is, as this voltage goes up, my net emitter voltage here is going up. Net emitter voltage is going up. Collector voltage is fixed at VCC, and therefore my collector emitter voltage here is dropping. Collector emitter voltage is dropping, and I must ensure that my transistor does not go into saturation region here. So that's why we've drawn a band here of around 0.2, and therefore what I'm interested in is that at its peak value it should not go into this particular band here. Okay, so that tells me as to how large a V0 I can get here. So straightforward now. All we need to do is to say this is the DC value of the emitter voltage VE plus V0. This is the peak value here plus V0 should be less than or equal to VCC minus VC sat. Right? So it should not go into this forbidden region here. And therefore, it tells you that your V0 output voltage has to be less than VCC minus VC sat. And instead of VE here, we have now written VE as in terms of ICQ here times RE. Okay? A drop here. ICQ times RE. So it tells you your output voltage will always be less than this value. This is coming from the fact that transistor should stay out of saturation region. Okay, so that's one constraint to keep in mind. There are multiple constraints. That's first constraint here. The second one is, look at this particular stage here, VB. So now, earlier I was looking at saturation. Now I'm looking at my amplifier from the input side here. And my focus is here, at this node here, VB. Is it true that this voltage at this particular point should always be less than VCC? My supply voltage is VCC here. Will this voltage, is it going to be always less than VCC? Yes or no? Yes? All of you are saying this voltage has to be less than VCC. Why? Note, if this voltage has to be less than VCC here, between here and here, what do I have? Between base and emitter, I have 0.7 volt drop, which means you are saying that this voltage has to be less than VCC minus 0.7. Alright, but let me show you here. Alright, so the argument here is as follows. The argument is whatever is the voltage at the base, whatever is the voltage at the base here, so I've drawn a voltage at the base, and when I apply an input voltage here, what that input does is it adds to the base here. It adds to the base voltage here. So my net voltage at the base becomes this one here. And what many of you are agreeing at present is that the voltage at the net voltage at the base node must be less than VCC here. And therefore it's telling you is that VB, whatever is the DC value of VB plus Vin should be less than VCC. If that is true, then what you are saying is that your Vin should be less than or equal to VCC minus VB. And note what Vin is what? Vin is the sinusoidal voltage here. Is the signal here. Vin is the signal here. And if Vin is less than or equal to VCC minus VB, what will V0 be? It's a common collector amplifier. So first, to the first order approximation, V0 is nothing but equal to Vin. Gain is practically equal to 1. So V0 equal to Vin. So what we are saying is that this value V0 will be less than or equal to VCC minus VB. So you're bringing out another constraint on your output voltage swing. You're saying V0 has to be less than or equal to VCC minus VB. Okay. But before we go to that, let's look at the following here. So here is an example. I have 28K, 35K, all this amplifier is there. VCC is 12 volt. It's not shown here as 12 volt. Now, the way it is biased, this value is 6.17. 6.17. Now, all of you are saying that I cannot get a voltage larger than 12 here. Which means I cannot apply 7, is it? If I apply 7, what will I get? Note what happens to the sinusoid. The sinusoid goes here and adds to this one. So, the peak value will be 7 plus 6, 13. And on the negative side, it will go 6.17 minus 7. So, it will go some negative value here. Is that not possible? All of you are claiming that it will not go above VCC. Alright, let's run the simulation and see. It goes fine. It goes to 13.167. It goes to minus 0.8. It goes to, why were you all saying that this voltage cannot go above VCC? It is going above VCC here. No? It's going to 13.167 and it's falling to negative also. The capacitor allows you to do that. Alright, think about it. So there is no problem in this particular node going above VCC here. There is no problem. In fact, this node, even though what you are seeing here is I have a DC here, 12 volt and a ground here, that doesn't mean that the value signal here cannot go negative. It is going negative here. It is going negative here. When you have a capacitor, you can get all of these things. Okay, think about it, how to explain what is happening here. So the point is, my whole argument was based on the fact that the net voltage at this particular node cannot go above VCC, right? But we are seeing it can go above VCC. There's no issue here. All right. So the problem is not in a stage like this here. The problem is not in a stage like this, which is capacitively coupled. Many times what happens is, my previous stage is coupled not through a capacitor, but is directly coupled to my next stage here. Is directly coupled to next stage here. In this case, note that if I'm talking about the base voltage earlier was VB, in this case, V in plus VB cannot go above VCC because it's coming from a previous stage like this here. In the common, let's say this is a common emitter stage, which is driving my common collector. This input cannot go above VCC here, but then the transistor gets cut off and all of that. It can't happen. That we've already seen here. So if it's directly coupled, my voltage at the node here at the base, V in plus VB, cannot go above VCC. And all of that I said is true. But if I couple it capacitively, then as I've just shown you in the previous case, it can go up to 13, can go up to 14. There's no issue at that side. Okay. At least from the base side here, the fact that we can build up voltage at the base to whatever value we want. Okay. So this constraint will come when I couple it directly rather than through a capacitance here. And then this issue is there. VB plus Vin has to be less than VCC here. And therefore, my VB here, base voltage, note that base voltage is equal to ICQRE. Base emitter voltage plus ICQRE here. That's the base voltage here. Vin is practically equal to V0. So we get a constraint which is here. That V0 has to be less than or equal to VCC minus VBE minus ICQRE. So we get a constraint on how large my output voltage can be. Coming from the fact that the net voltage at the base has to be less than equal to VCC here. So we get two constraints now. We have identified two constraints. One is coming from saturation, which says V0 must be less than or equal to VCC minus ICQRE minus VC sat. The other one is coming from here, which says V0 is less than or equal to VCC minus ICQRE minus VBE. Obviously, if you compare these two, what will determine my swing is the second one, because VC sat is around 0.2 or 0.3 and VBE is 0.7. So this is more important for me rather than this one. Okay, so if I'm directly coupling my input to my next stage here, this becomes an important point. Okay, we don't need to bother. On the other hand, if you're doing it capacitively and there's no constraint on how large VB can go, then you have to worry about the first term here. All right, there are more limits here. The other limit comes from output current capability here. My amplifier, so note that what we are wanting is to build up voltage here across a load resistance RL. So I'm wanting to build up swing here across a load resistance RL. And if I build up large swing here, the large swing requires a large current also. And if it requires a large current, and my stage must have the capability of driving that much current. Okay, so let's look at what are the problems here. So the idea is that my amplifier should have enough current to drive into my load here. Okay, so look at this particular part here. Let's see the case when my voltage is going high. Voltage is going high here at this point here. When the voltage is positive, the current in my load is flowing down. Current here is obviously always flowing down, and the other current is here. So if we look at the KCL at this particular node here, this current, which is the collector current, is equal to, note the voltage at this particular node becomes VE plus V0. VE is the DC value plus the AC value here, VE plus V0 divided by RE, that's this current, and the other current is V0 by RE. That's this current here. So this is the current balance that I must have. My transistor has to supply current here in this branch and in this branch here. So now the issue that we are saying is, what happens if you keep on reducing RL? If you keep on reducing RL, demand for current here is increasing, and will a stage come where my transistor will not be able to supply that current? If my transistor cannot supply that much current, note, if this requires, let's say, a current of 1 milliampere, and if your transistor can only supply 0.9 milliampere, then what does it mean? It means that the current available here is less than what is required here, and therefore, the natural consequence of that would be the output voltage will become less. If not enough current is available, V0 will not be equal to the value that we have. V0 will become smaller. Will that stage arise? Do you think that my transistor, a stage can come if I keep on reducing RL where my transistor, let's say, is not able to drive that much current? Will that occur? Is that situation likely to occur? Now, we have to look at this situation from both sides. We have to look at it when my swing is positive and when my swing is negative. Now, let me show you why this is not so much of a problem here. Suppose, for a moment, suppose that I don't have enough current here. All right. So let's say I'm applying 1 volt here. I have 1 volt input voltage, and obviously I would require 1 volt here. Okay, I would require 1 volt here. But suppose I don't have enough current in my amplifier. Enough current meaning I don't have enough current here. And therefore, the voltage doesn't reach 1 volt. It reaches 0.7. Suppose the voltage is not able to, I don't have enough current, the voltage reaches 0.7. What happens then momentarily? This voltage, so note what happens here. What is the net base emitter voltage? The net base emitter voltage that you see here is equal to DC plus a small signal AC. That's the net base emitter voltage. Okay. Remember, every voltage has a DC part and a sinusoidal part here. So VB will be equal to 0.7 plus small signal VB. Small signal VB is what? I've applied 1 here, and we are saying this is 0.7. So what happens to this value? 0.3. It becomes 0.3. And now note, how does current increase with voltage? With base emitter voltage? Exponentially. So what happens is, if this voltage falls below this one significantly, it doesn't reach 1 volt, what happens is a base emitter voltage develops here that you see here, and the current follows exponentially with that. So current immediately becomes larger. It doesn't allow this voltage here to become significantly less than 1 volt. So this problem is not likely to occur. Anytime that this voltage, let's say, falls below this one, a base emitter voltage develops which is high and, pumps in more current and causes this voltage to rise to the value that is there. So it's not likely to occur unless you make RL so large or so small that, inside the transistor, for example, there's a maximum current limit coming from power dissipation and many other limits here. If you don't exceed that, then this circuit, there's no issue. There's no problem. In the sense of my amplifier will be able to pump in more and more current here into this particular one as you reduce RL. Till the point where you don't violate the internal current limit and power limit of your transistor. The problem doesn't come in the positive swing actually. The problem comes in the negative swing. So let's look at the negative swing part. Alright, there should be enough drive current. So now we are talking about the negative side here. Now negative side, remember, this becomes negative. So now my current balance is as follows here. Transistor obviously keeps on pumping current in the downward direction, collector current. Current that goes in here is also here. But because voltage is negative, the current goes up here. So now my current balance is as follows. This current that you see here plus this current, the sum of these two currents must be equal to this current. That's my current balance. So this current that you see here becomes VE minus V0 by RE. Why? Because VE minus V0, we are going in negative direction here. So that's VE minus V0 by RE. So the first current, this current, is equal to V0 by RL. That's this current here. V0 by RL plus IC here. Plus IC here. Okay. Now I can write this down as VE, I've written as ICQRE minus V0 by RE must be greater than or equal to V0 by RL. What is the best that you can do about collector current? If you look at this particular equation, when will your V0 be maximum? When IC is minimum. So the best that you could do, the best that you could do is you could make, because remember now what is happening is the sum of these two currents is equal to this one. So the best that you could do is make your collector current negligible. Make your collector current negligible. If you make your collector current negligible, let's say, or what we are saying is ICQ minus RE minus V0 by RE must be always greater than V0 by RL, because IC has to be some positive value. Otherwise my transistor is in cutoff state. So it has to be greater than or equal to 0. So I can write this condition, and this condition then tells me V0 is less than or equal to ICQ RE parallel R. It tells you that your V0 always has to be less than this. This condition. That is telling you a limit on V0, which is coming from where? Coming from current driving capability. It all depends on, there's a limit on V0 that you get depending on how you have biased your transistor here, depending on the ICQ that you bias here. The larger the ICQ, the greater the capability of your amplifier in building up value of V0. So this is the limit that is coming here from current drive capability. V0 is less than or equal to ICQ RE parallel RL. So you can note here that if you, for example, if I keep on making my RL smaller, here, RL times, so this quantity keeps on getting smaller, and V0 also keeps on falling here. And so this limit is not coming from saturation. It's not coming from, it's coming purely from looking at the current balance here, from the current driving capability. And it's related to how your amplifier is biased, depending on the current at which it is biased here. So another limit on V0 that we are getting from the current driving capability. So it's coming from where? From the negative swing. From the positive swing, it doesn't really matter. My transistor is able to supply enough current. But in the negative case, all that my transistor can do is IC can become negligible, and then I have this balance here between these two limits here, and I get V0 less than or equal to ICQ RE parallel. Okay. Now, the other one, some of you may be wondering, what about harmonic distortion? This amplifier, note that when I have a capacitor under AC, it's a short, I have a resistance in the emitter. And I've already shown you that when you have a resistance in the emitter, what you have is, there's a negative feedback. And the other way of looking upon it is as follows. I've already showed you that, you have all of this that you see here, Vs is equal to all of that. But Vs is practically equal to V0 in common collector amplifier. So what happens is, all this part that there may be nonlinearity here in all of this, but if V0 is equal to Vs, it doesn't really matter. V0 is practically equal to Vs, so my amplifier is highly linear amplifier. So one way of looking at it is simply from small signal which says V0 is equal to Vs, Vs equal to V0. So no nonlinearity. There's nothing GM. Remember, GM and all of that is the place where nonlinearity enters here. It's the relationship, this relationship, that between base emitter voltage and current, I have GMVB. It is here that I have nonlinearity entering. But if this doesn't play any role, V0 is equal to Vs, it doesn't really matter. It's a highly linear amplifier. The other way of looking upon it is this resistance here, it builds up a negative feedback and therefore reduces distortion here. So distortion is not an issue. Transfer characteristics is quite linear, and I don't have to worry about it here. All right, so let me, I'll stop here with this example. So it's the same amplifier shown here, the biasing condition, gain is 0.99, Rn and all that. Various constraints on swing. From the fact that the voltage here, voltage has to be less than the supply voltage here. We get a constraint of 5.85 volt, and from current driving capability, we get a constraint of 3.2, and therefore my swing is determined in this case by current driving capability of 3.2, and this is what happens here. Note, so what I've done here is I've applied 3 volts here. So my analysis tells me that my maximum swing is 3.2, determined by current driving capability. So to test it, I applied 3 volt here, and I expect Vs equal to V0. So note that there is a V in also here, 3 volt, V0 is also there, perfect 3 volt. harmonic distortion very small. Now if I increase my V in a little bit to 3.5, you can see the problem that is occurring on the negative side. And why is this occurring? It's occurring because of I don't have enough current in my system. My ICQ is not enough. I don't have enough current, and that's why my voltage is getting clipped. It's not coming from saturation. It's not coming from my voltage not able to exceed VCC. All of that is not the issue. The issue is the current here. And that's why I get a clipping here. And the moment clipping occurs, note that harmonic distortion starts increasing, 2.6. Yeah. So due to current limitation here, so let's stop here and